When you press play on a 4K high-definition video, the playback appears instantaneous. Maintaining that high-resolution stream requires a series of engineering precision strikes against the physical chaos of the global internet. This environment is defined by heterogeneity. The internet is a patchwork of unequal devices and wildly fluctuating connections where no two users share the same network conditions. We see this contrast when comparing a 4K smart TV on a stable fiber connection against a mobile phone on a weak 4G signal. The fiber connection can sustain a heavy, constant data flow, while the mobile connection might drop or spike every few seconds. Because of this inequality, a traditional one-size-fits-all broadcast is physically impossible. Attempting to send a high bitrate stream to a congested mobile link results in a systemic failure of playback. Legacy streaming systems utilized constant bitrate, or CBR. In this model, the video's data output remains fixed at a specific rate, regardless of the scene complexity or the state of the network. CBR fails during periods of network congestion. If the available bandwidth drops below the video's fixed rate, the packets are delayed, leading to the buffering lag that interrupts the user's experience. Variable bitrate, or VBR, was an attempt to optimize this by adjusting the data size based on the video content, using more data for action scenes and less for static ones. However, VBR still cannot account for sudden, unpredictable network slowdowns. As long as the server blindly dictates the transmission rate, seamless playback is impossible on an unpredictable network. To solve this, the mechanism of control must change. To manage network heterogeneity, modern systems strip control away from the server and give it to the client device. The standard protocol enabling this is DASH, Dynamic Adaptive Streaming over HTTP. Under the DASH protocol, the server no longer hosts a single continuous video file. Instead, the server partitions the video into thousands of brief, independent chunks, usually just a few seconds long. The server then encodes every one of those chunks at multiple quality levels, from 240p up to 1080p or 4K. The server provides a roadmap via an XML manifest file containing URLs and bit rates for every chunk. The client continuously calculates its real-time bandwidth, reads the manifest, and pulls the highest quality chunk it can handle. If bandwidth drops, it automatically requests a lower quality chunk. The client also manages buffering, stockpiling a few seconds of these chunks in local memory. This ensures playback continues even if the network speed fluctuates briefly between requests. DASH replaces the passive broadcast model with an active negotiation. The user's device drives the process, adjusting to network constraints chunk by chunk. Shifting logic to the client solves the bandwidth problem, but it creates a new challenge of scale. Millions of clients making simultaneous requests to a single central server will quickly overwhelm that server's capacity. Concentrating traffic on one hub causes failure and massive latency. The solution is a Content Delivery Network, or CDN. Akamai pushes servers deep into local ISPs for low delay. Limelight places larger clusters regionally, adding slight latency but easing management. By distributing these servers, the network ensures that video traffic lives as close to the end user as geographically possible, preventing a collapse of the core internet backbone. This decentralized infrastructure raises a mechanical question. If identical copies of a video are scattered across hundreds of global servers, the browser needs a way to identify which specific local edge server is the most efficient to contact. The user's local DNS contacts the website's authoritative DNS. Instead of returning a final IP, it redirects to a CDN DNS. This CDN DNS analyzes the user's IP, pinpoints the closest available server, and delivers that local IP so the browser fetches chunks directly. This redirection mechanism happens in milliseconds. It silently hijacks the request to ensure that the massive data transfer remains local and efficient. We can see these protocols integrated at a massive scale by looking at Netflix, which accounts for a significant portion of all internet traffic. Netflix manages its own proprietary CDN called OpenConnect, rather than relying on third-party providers. Netflix pre-positions its content at these OpenConnect nodes during off-peak hours, ensuring that movies are already waiting at the network's edge before a user even hits play. When a subscriber starts a movie, the DNS routing points them to the nearest OpenConnect node, which then serves the manifest file and the specific dash chunks required for that movie. This architecture demonstrates the integration of geographical proximity and client-side adaptive logic to deliver high-resolution video at a global scale. While Dash and CDNs operate at the application layer, they are ultimately limited by the transport and network layers of the Internet. The delivery of video chunks relies on TCP congestion control, which uses exponential growth during slow start and linear increases during congestion avoidance to maximize throughput without causing packet loss. At the routing level, autonomous systems use policies like hot potato routing. These routers choose the closest possible exit point to hand off the traffic, minimizing the time any single network must carry the high-volume video data. Underlying these decisions is Dijkstra's algorithm, which routers use to calculate the shortest paths through the network graph by building a spanning tree step by step. The seamless playback of a modern stream is the result of a continuous microsecond by microsecond interaction between application logic, physical geography, and core networking protocols.